I'm now going to branch into an area of probability that may or may not be discussed in your particular finite mathematics course, but you may run across it in another business or math related course at some point. What we're going to talk about is Markov chains. And Markov chains are related to the possible states that a system could be in. So let's just look at some physical states, physical systems and their states. So let's look at an example. Let's say each day the trading market is open, a stock is going to increase, decrease, or remain the same, unchanged. So the physical condition of the stock has three states. It could increase, decrease, or no change. Another example, a businessman that sometimes travel can either be thought of as in town or out of town. So that could be the two states. During radiation treatment, a tumor can increase, decrease, or not change in size. Three states again. During an election, we could describe the states of a voting precinct as predominantly Republican, predominantly Democrat, or predominantly other. Again, three states. Now, it says here that if a system evolves from one state to another by way of the element of chance, then the system's progression through the sequence of states is called a stochastic process. So, for instance, a stochastic process would be if the stock goes from an increasing to a decreasing state, or if the businessman goes from in town to out of town, or the tumor goes from increasing to decreasing in size, and so forth. So those would be considered stochastic processes. Now let's consider this example below. In this example, a company markets a cell phone, and we'll call it brand A. And we'll say brand A currently has 10% of the particular market that we're talking about. So the company hires a market research manager to estimate the portion of the market that it might acquire in the future by launching an aggressive sales campaign. So the manager uses different things to do this. He can do test marketing, he can present polls to the population and questionnaires or whatever, but he does these things to try to predict what effect this aggressive sales campaign would be on the market share. So let's say they find that those already using brand A, for anyone that's already using brand, there's an 80% chance that they will continue to use the brand. So in other words, they will buy the brand when they upgrade. They also find that a person not using brand A has a 60% likelihood of switching to brand A when they upgrade. So we actually have two possible states. We'll say A is the state that they use brand A when they upgrade, and A prime is that they use another brand when they upgrade. The probabilities can be represented visually by what's called a transition diagram, and we can then put the data in a transition matrix, or the probabilities in a transition matrix. So this circle are those people that are using brand A. Well, we saw that there's an 80% chance that they will continue to use brand A. So in other words, when they upgrade, you can see the probability that they come back to brand A is 80%, or 0.8. Now, if the probability that they return to brand A is 80%, then the probability that they do not return, or they go to some other brand, go this path, that would be a 20% chance. Now let's look at those that are not using brand A. Well, it says up here they have a 60% likelihood of switching brands. So let's draw the path from not A to A, and we see that probability would be 0.6, which means there's a 40% probability that those using a brand other than A will continue not using brand A. So that probability would be 0.4. Well, then we can do this transition matrix. And so let's say they have a current state of A. The probability that they return to A is 0.8. The probability that they leave A is 0.2. If they start with a brand other than A, then the probability they will return to A is 0.6, and the probability that they will stick with the other brand is 0.4. And we're going to call this state matrix the matrix P. We can also write a state matrix S0. Now the reason for the 0 here is this is the initial state matrix. If you go back and read the problem, the company has a 10% market share, so 10% are using brand A, so that would mean that 90% are using some other brand. And this is called the initial state probability matrix. If we do a probability tree, you can see that in the initial state, the probability that they stay with brand A is a 10%, and the probability that they leave brand A, use another brand, is a 90%. Okay, now, in the next state, in other words, when they upgrade from this transition matrix here, we can see that if they start with brand A, there's an 80% chance that they will continue with brand A in the next upgrade, and there's a 20% chance that they will switch to another brand. If they start with a brand other than A from that same transition matrix, we see there's a 60% chance that they will upgrade to brand A, and there's a 40% chance that they will continue to use a brand other than brand A. So A0 is the first state and A1 is the second state. So this is A0, this is the first state of A, this is the initial state of A, this is the first state of A, and A0 prime is the initial state of A prime, and A1 is the initial state, is the state given that they started with A prime, and then A1 prime is the state given that they started, A1 prime is the fact that they stayed with the other brand given that they started with the other brand. So over here you can see, using conditional probabilities, the probability that they go with A1 given that they started with A0 is, in the initial state, is 0.8. And the probability that they stay with A1 given that they didn't start with A is 0.6. So the other branches are just the complements of those values. Now, using the probabilities that we learned in the previous chapter, we can find that the probability of A1 would be the sum of the products of the paths that lead to A1. So the probability of A1 would be 0.1 times 0.8 plus 0.9 times 0.6, and that gives a 0.62. So the probability that they continue using brand A in the upgrade is 0.62. Now the probability they don't use brand A in the upgrade, you can just use the complement 1 minus 0.62 to get 0.38, or you could do it like I did this first one and just say, okay, multiply the paths from all the paths to A1 prime, so that would be 0.1 times 0.2 plus 0.9 times 0.4. But either way, you'll get 0.38 for the probability. So from those probabilities, we move from the initial state matrix to the first state matrix. And so those probabilities give me the probabilities that they will use brand A or not use brand A in the first state. Now, we can also talk about other states. What's very interesting here is if you took the initial state matrix and multiplied it by the transition matrix, 0.1, 0.9 times this transition matrix, you actually get the first state matrix probabilities. It's just magic. So anyway, if you want to get the second state probabilities, you can take the first state and multiply it by the transition matrix, and you can do the multiplication by hand or by a calculator, but that's what you would get. So that the second state matrix would be, there's a probability, 72% probability that they would upgrade a second time to brand A, and a 28% probability that they would upgrade to a different brand the second time around. And if you wanted to go to the third state, then multiply S2 times P to get the third state. And notice here, the probability that they upgrade to A, stay with A in the third state, is about 74% and 26% for them not to stay with A. Now, to get higher states, we're going to discuss this a little further. Okay, let's define what a Markov chain is. The sequence of trials using the cell phone brand above is a special stochastic process called a Markov chain. A Markov chain is a sequence of experiments or trials or observations such that the transition matrix from one state to the next is constant. So remember, our transition matrix was that with the four values, 0.8, 0.2, 0.6, 0.4, and it never changed. So given a Markov chain, let's say with n states, a kth state matrix is a matrix of this form, S of k, where it's just a row of the possible states. Now each value is the proportion or percentage of the population that is in state A after the kth trial. Another way to say this, the probability of a randomly selected element of the population being in state I after the kth trial. Now the transition matrix is a constant square matrix, we'll call it P, of order n, so that's size n by n, such that the entry in the ith row and jth column indicates the probability of the system moving from the ith state to the jth state on the next trial. And the sum of the entries in each row is 1. So look at our simple 2 by 2 transition matrix here. And this is a different transition matrix. But here, the probability of going from state A to state A is 0.75, and from going from state A to state B is 0.25. The probability of going from B to state A is 0.67, and the probability of going from B to state B is 0.33. And this matrix is a constant square matrix P of order 2, and you can see I've already described the states there for you. And remember, the entries in the k state must be real numbers from 0 to 1, and remember the rows have to add up to 1. So you notice the first row, 0.75 plus 0.25 adds up to 1, and 0.67 plus 0.33 adds up to 1. And in the next video, we'll take a deeper look at examples of some Markov chain examples.